In this case, where our motion is not uniform across our imaging sensor, some of the key questions are, how far do objects move during the roll of the shutter? So as that shutter is moving from top to bottom, how far do the objects actually move during that time? Also, how many rows of the sensor do the objects cover? We can imagine that smaller objects are going to incur less artifacts than larger objects. So the key point is comparing the size and speed of objects to the speed of our rolling shutter. Here we've got a nice T for tungsten sample, which is going to move slowly from left to right, and a much faster rolling shutter, which is going to attempt to sample it. In this case, our shutter speed is much greater than our object speed. And as we can see, providing our shutter speed is much faster, we get an undistorted result. You can imagine that if this T for tungsten was 10 times taller and the red line was moving just the same speed, we might start to end up with artifacts even at this speed, because the height is also important. But in this case, our shutter is more than able to keep pace. However, if the object speed starts to approach or even exceed the shutter speed, we can end up with just the kind of artifacts that we've shown. If that's a horizontal motion, the artifacts might look like this. And hopefully you can see from the interaction of the red line and the T how this image is formed. If, on the other hand, they are vertical distortions, we can end up with this stretching of the object. If the motion was in the opposite direction to the rolling shutter, then the stretch would be in the other direction, would be compressed. Quick note to remember that the speed of our object motion we can characterize in pixels per second, as we introduced earlier in the presentation, but our speed of our shutter in pixels per second is just 1 divided by the line time. So it's really simple to work out once you have that line time. So the key question is, how fast is your sample?